Hey guys, Mr. McKinney here, just doing a quick review of AP Unit 8, which is the last unit in the AP curriculum. It's on applications of integration. This will cover stuff that we did in Units 7, 9, and 10. So AP Unit 8 does not match up with our Unit 8, it matches up with our Units 7, 9, and 10. Okay, so the first thing is average value. And I grouped together average value and the average value theorem. Now, sometimes these are called mean values or mean value theorem. I kind of like to think about mean value theorem as the one for derivatives and average value theorem as the one for integrals. You can go back and watch the other MVT videos if you need to review the other MVT. So as long as you can integrate a function, so if you can integrate it, which it doesn't necessarily need to be continuous. So for example, you can integrate a step function because you can find the area underneath each step. So as long as you can integrate a function, you can find the average value by using this formula. So you basically divide by the width. B minus A is the width of the whole interval, and this integral is the area. So if I do area divided by width, essentially, I'm going to get the height, and it's going to be the average height. Now, the mean value theorem or the average value theorem for integrals basically says that if f is continuous, so not just being integrable, but also being continuous. If it's continuous, then we're guaranteed to hit the average value somewhere on that interval. So this part is exactly the same as this whole part over here. But just like the MVT for derivatives, as long as f is continuous, then we're guaranteed to hit the average value. Now, this does not apply on a step function. For example, here, if this step's at 1 and this step's at 2, the average value is going to be 1.5. And I never actually hit 1.5. But if the function's continuous, then I'm guaranteed to hit the average value somewhere. So average value, you do 1 divided by the width times the area. We've talked about position, velocity, and acceleration with derivatives and how to move around with derivatives. So now let's talk about how you would apply them with integrals. I took this part off the cheat sheet. There's two main ways that you'll see integrals. So one way is to go from velocity to either total distance or displacement. This is the one that shows up most common on the AP exam. They'll ask for the total distance that a particle travels. It'll give you the velocity, and it's almost always on the calculator portion. So you're going to hit Math 9. If this was not on the calculator portion and they gave you a graph, you'd just be looking at the area, but you'd make everything positive. But this is usually on the calculator portion of the AP exam, and you can use Math 9 to calculate this. The other way that you see integrals with position, velocity, and acceleration is finding a future position. So this is what we have off our cheat sheet. This was from other slides that we've done in this class. So basically, a future position or amount is equal to the initial position or amount plus the accumulated position or amount. Now, the derivative of position is velocity. So you can think about it as the integral of velocity or as the integral of the rate of position, which is velocity. But this is not just limited to position. You can do this with any amount. So any future amount is going to be the initial amount plus the accumulated amount. And the accumulated amount is always going to be an integral of a rate. If you integrate a rate, you get an amount. Okay, the rest of this unit, oh, and I put in a couple of examples here. So if you're trying to find the positions and you have initial positions and velocities, then you're just going to do initial position plus the integral of velocity. So that's like what we did here. And then I put this example in, which is a total distance problem. So again, this is likely going to be on the calculator portion. So you don't have to really show any work. You just have to show the integral that you typed into your calculator. The rest of this unit was basically on area and volume. So let's talk about area first. So when we're looking at area, most of the problems you'll be able to do most easily as a dx problem. So you want to do the top function minus the bottom function, and then the limits are wherever they intersect. So for this particular problem, the top function is f and the bottom function is g. So to find this area, I would do the integral from 1 to 3 of f minus g. Some problems will be easier if you turn them into a sideways problem and you do right minus left. So for example, if I were to graph these three graphs, so 4 minus 2x is a linear function that would cross at positive 4. These square root functions, so they're flipped horizontally, they would cross out here at 4, and it would look something like this. So we're trying to find the region in between there. Now technically you can do this problem as a dx problem, but it becomes much more difficult because you have to break it up into different pieces. So you would have to say something along the lines of whatever this number was, we'll call that A, and then whatever this number was, B, and then whatever this number is, C. So for the first integral, you'd have to do like y2 minus y1 between A and B, but then between B and C, you'd be doing y2 minus y3. So you'd have to set it up as two separate integrals. It could be done. You can always do area problems either way. They can be a dx or a dy. Sometimes it's easier to do it one way than the other, but with area, you can always do it both ways. So on a problem like this, especially when you see the positive or negative root, what you'd want to do is solve them for x. So this equation, if I solved for x, so we'd have 2x on this side equals 4 minus y, divide by 2. So x would be 2 minus y over 2. And then both of these together are going to create the same equation. Because if I square it, it doesn't matter whether it's positive or negative. I'm going to get y squared equals 4 minus x, add the x, and subtract the y squared. So 4 minus y squared encompasses both of these. So if we're going to do it that way, then this curve would become like my x2. So instead of worrying about y2 and y3, this whole thing would just become my x2 curve. This one would be my x1 curve. And then instead of integrating along the x-axis, I would need to know what the intersection points were. And then I would just do the integral, let's call this one d and e. So we do the integral from d to e of right minus left. So my right would be x2, my left would be x1, and this would now become a dy problem. So with area, you can always do it either way. Sometimes it's easier to do it as a dy problem. When you're doing volume, you have to pay attention to whether you're going, like which axis you're perpendicular to for the known cross-section, or which axis you're rotating around for the disk method. So these problems you have to do one way or the other, depending on which axis you're perpendicular to. So this was not the first topic that we did, but it's listed first in the AP curriculum, and I think it's probably the one that's most common to show up. So sometimes they will just give you this area formula. So there's a problem on a recent year where they just told you that the cross-sectional area can be modeled by the formula A of x equals 1 over x plus 3. And then you can just plug that in. So you do v equals the integral from, let's say, 0 to 5, 1 over x plus 3 dx. Sometimes they will just give you the area formula. Sometimes they will give you a region and say the cross sections are squares perpendicular to the x-axis. In that case, you'd have to figure out what your function is and then find a formula for area. So if it was a square, it would probably be the function squared, because a side by side is the side squared. If it was like a triangle, maybe an equilateral, or not an equilateral, let's say it's an isosceles triangle, and one of the legs is in the region, then my area would now become 1/2 times f of x squared. So sometimes you'll have to create the area function if they tell you the shape of the cross section. Sometimes they just give you the formula for the area of the cross section. So if they just give you the formula for the area, just plug that in. If they ask you to, you might have to generate the formula. Now, if your cross sections are perpendicular to the x-axis, it's a dx problem. If your cross sections are perpendicular to the y-axis, it's a dy problem. The other two topics in this unit are the disk method and the washer method. So you use the disk method if the region that you're rotating touches the axis of rotation everywhere. So for example, here, the region in blue that I'm rotating touches the x-axis everywhere. So at every point, I'm taking a radius, which is basically just my function, and then I'm rotating it around to create a circle or a disk. So this radius turns into a disk. At every point, this radius is turning into a disk. So if I rotate around a horizontal axis, so the x-axis or like the line y equals 2, keep in mind that the x-axis is the line y equals 0. So if it's a y equals line, that's a horizontal line, it's a dx problem. If you're rotating around a vertical axis, like the y-axis or x equals 2 or x equals 0, which is the y-axis, then it needs to be a dy problem and everything needs to be in terms of y. Either way, you're going to do pi r squared because you're adding up a bunch of circles. This pi can start out inside or outside because constants can move in and out of the integral. For the radius, make sure that you're always taking into account the axis of rotation. So if we're rotating around the x-axis or the y-axis, it's just going to be f of x minus 0. So it'd be like f of x minus 0 squared. But if you rotate around the line y equals 2, then you need to make sure that you have f of x minus 2 squared. So the radius is not always just the function. It's the function minus the axis of rotation. So if you're rotating around either the x-axis or the y-axis, then this is going to end up being 0 and it won't affect anything. But you need to always be thinking about what is the axis of rotation. It should always be a function minus the axis of rotation. So again, use the disk method if your region touches the axis of rotation everywhere. If your region does not touch the axis of rotation everywhere, so for example, if I want to take this little leaf looking thing and rotate it around the x-axis, this is not touching the x-axis everywhere. So I'm not going to get disks. I'm not going to have solid disks. Essentially, these are going to be washers. So we're going to have like a piece, but there's a gap in the middle. And sometimes if you visualize it on its side, it's a little bit easier to see these washers. So we're adding up a bunch of washers. And if you think about what a washer looks like, it's a big circle with a little circle. So you've got your little radius on the inside and your big radius on the outside. To figure out the area of a washer, you would do pi times the big radius, the big circle, minus pi times the little radius. Now you can pull the pi out of both of them and put it out front. Keep in mind that for your radii, the big radius and the little radius, your outer radius and your inner radius, each of those needs to take into account the axis of rotation. So we just see big R squared and little r squared, but if we were actually doing this problem, and let's say we were rotating around the line y equals 5, then for the outer radius, I would have like f of x minus 5 squared. And then for the inner radius, I would have maybe g of x minus 5 squared. So make sure you take into account your axis of rotation. Now, it should be big radius squared minus little radius squared. Don't do big minus little squared. So the axis of rotation should be inside the squared, but you need to square the two radii separately because it's coming from this idea for the area of a washer. Again, if you rotate around a horizontal axis, then it's going to be a dx problem. If you rotate around a vertical axis, it's going to be a dy problem. Now, I didn't do a lot of in-depth examples on these because we have videos recorded. So go back and watch those videos again if you have questions on the minute details. I just wanted to go over how to figure out which type to use and the basics. So hopefully this was helpful. Good luck studying, guys.